Multivariable use of the chain rule is a direct extension of the single variable chain rule. However, when we do it with multivariables, we need to be careful about using partial derivatives. When we're doing it with a single variable, the partial derivative acts mostly like the ordinary derivative, because there's only one variable to hold steady. Because there's no variables to hold steady, and only one variable to take a derivative of. Okay, in this example, we have x squared, x times y to the power of 3, with x and y defined as such. To find the time derivative of z, dz dt, we first deal with x, partial derivative of z with respect to x, dx dt. This is equal to, we take the partial x derivative, which means we treat y as a constant. We hold it constant. So we get y cubed. The partial derivative of x with respect to time is cosine t. Next, we repeat this for y. We take the partial derivative of z with respect to y, dy dt. Okay, when we take the partial derivative with respect to y, then we treat all other variables as constants, which makes taking derivative very easy. We get 3xy squared times the ordinary derivative of y with respect to t, which gives us 2e to the 2t. Our last step involves replacing x and y with their appropriate values, functions, with respect to t. So y cubed becomes e to the 2t cubed cosine t plus 6, 3 and 2. X is sine t, y squared, e to the 2t squared, e to the 2t. Now this function could use quite a bit of simplification. In particular, we can write e to the 6t bracket cosine t plus 6 sine t. That is the time derivative of z. If we repeat this for a different function, z equals y times e to the power of 8x, with x and y defined as such, then we can use our expansion similarly. Namely, dz dt equals partial of z with respect to x dx dt. And of course, this doesn't only work for x and y, but for any variables we may have. There is an excellent example in the book with regards to physical chemistry and holding temperature and particle number and such constant. In this case, in our particular example right here, we'll take the partial derivative of c with respect to x. That is, we hold all other things constant. Y e to the 8x times the time derivative of x, which is 6t minus 1 plus the time derivative, the y derivative of z, partial y derivative of z, which means we treat x as a constant. It takes the derivative of y, which gives us e to the 8x. Now the time derivative of y is simply t. We can simplify this as e to the 8x y 6t minus 1 plus t finally, we need to substitute in our values for x and y. We could leave it as this, I suppose this is true, so let's say this is a false function, but we want it properly in t. So I'll substitute in e to the 8x, which is 5 minus t plus 3t squared times y, which is 1/2 t squared 6t minus 1 plus t. While further simplification is almost always possible, that is sufficient for our purposes.